Thinking about UV space, if we have a particular gradient, that gives us a line. That's what this red one shows us. But suppose we have another gradient, okay, but in the same little window. Well, that gradient would give us a different line. So this is gradient 1, this is gradient 2, over within the same window, and then here's gradient 3, and it gives us a different line. Clearly what's going on is if I have a bunch of these different gradients, they're all going to intersect at the point. That point is the correct UV. So as long as we have different gradients within the window, we can get a solution. We've seen this before, haven't we? Here is the equation we just showed you, A transpose A times E equals negative A transpose B. All right? When can that be solved? To just solve this, we would want A transpose A to be invertible, right? Because if it's invertible, I just multiply both sides by that, and I come up with a solution for D, okay? Well, when are matrices invertible? Well, from our linear algebra, we know that they need to be what's called well-conditioned. If they're not well-conditioned, then the inverse is unstable. And basically, you can look at the eigenvalues, all right? And the ratio of the largest eigenvalue to the smallest eigenvalue shouldn't be too big. That's from your conditioning. In fact, if the second eigenvalue were 0, lambda 1 over lambda 2 would be infinity, and that'd be awful. All right? So what we want are eigenvalues that are, approximately the same magnitude. Okay, so that will make it solvable. But wait. We also know when this should be solvable from the geometric demonstration we just did. This whole problem should be solvable as long as there are different gradients within the window. Because if there are different gradients within the window, then we get those intersections of those lines in UV space. So does this remind you of something, gradients and eigenvalues? Of course it does, because you're like right on the ball, all right? You remember our Harris corner detector? This matrix, A transpose A, that is the second moment matrix of the Harris detector. And if you remember, we looked at the eigenvectors and eigenvalues of that matrix to know whether or not something was a good corner.